Hi, my name is Victor Young,
My name is Forrest Young.
and this is our research paper for the Davidson Fellows Scholarship. From Risk to Action, Time Series Prediction of Respiratory Support Requirements in Sepsis Patients.
Globally, sepsis is the leading cause of morbidity and mortality, a fifth of all global deaths. And lung failure is common in sepsis. It requires early and precise decision making. The current modes of respiratory support in the ICU are along a graded ladder of support. First, there can be no respiratory support or oxygen,
Which is a face mask with low flow,
high flow nasal cannula,
which is heated humidified oxygen,
non-invasive ventilation,
which is a tight mask with a CPAP or BiPAP ventilator,
and invasive mechanical ventilation,
which is endotracheal, hence the name invasive,
and even tracheostomy.
which is surgery to open up the trachea.
Invasive mechanical ventilation, the main goal of our study. It carries significant iatrogenic risks, so we do not want to let a patient get on it too soon. We also do not want to let a patient get on it too late. Both leave irreversible risks. So we need next day prediction of respiratory support requirements to add actionable bedside value. In the USA alone, hospital-related costs are tens of billions each year and rising. In high-income countries, data shows the same.
Okay, so now let's start with our project. Let's start with the data sets. 3 years ago, we enrolled in the University of Utah's high school university program, and we successfully got access to the MIMIC-4 dataset, which is very professional. It's from MIT, and it contains de-identified clinical data on over 50,000 ICU patients. And for external validation, we used the eICU Collaborative Research Database, and for both, we completed training under the CITI program. Now, let's look at our study workflow. On the left, you can see our project from MIMIC. First, we excluded samples, patients, with more than 30% of characteristics missing, and we also excluded samples with an ICU length of stay of less than 48 hours. Then, we made the length of stay from 2 days and capped it at 14 days. Finally, we arrived at around 5,000 sepsis patients. For training, internal validation, and internal testing, we first engineered our features, we constructed some of our own temporal features, then we selected the most important features. Next, we trained 5 machine learning models, and we tuned their hyperparameters using Optuna. And from all of these, from the performance in the internal test set, we found the best model. And then we did external validation using eICU data, and finally, we performed SHAP-based model explanations. So let's look at each step. First, let's look at pre-processing and feature engineering. In order to predict next day respiratory support, our targets, which were O2, HF, NC, NIV, etc., we aligned the features with the targets so that the features of day T predict targets of day T plus 1. Next, for MIMIC data, we used a 70-15-15 ratio for splitting. And finally, on the bottom, you can see some of our various ways to pre-process data, like filling missing dynamic features using forward filling missing static features using KNN, standardization, and one-hot encoding. Next, we added our own temporal features because it is very hard for machine learning models to extract temporal information from temporal features. And you can see some of our examples, like lagged values, first order differences, rolling statistics, mean, standard deviation, min, max, etc. History features, like if the patient used invasive ventilation in the last day or the last 3 days, etc. Finally, we selected the most important features, first to enhance model stability, but also to decrease multicollinearity and prevent overfitting. To do this, we trained a multi-output light GBM model, and we also, an additional detail is that we slightly upgraded respiratory related features because, by common sense, those features will contribute a lot to the level of respiratory care even if the light GBM model does not recognize them. Finally, after selecting the top K features per class and the top M global features, we got a maximum of 30 features.
For training, we trained 5 machine learning models: XGBoost, Random Forest Classifier, CatBoost, LightGBM, and SVM. The first 4 are tree-based, and the last one is kernel-based. We used Optuna's Bayesian hyperparameter tuning to tune their hyperparameters, and we found a problem, which is a sphere class imbalance. Only 32 cases of invasive mechanical ventilation were recorded. But we fixed this easily by using training-only class weights. We want to emphasize mistakes on IMV so that the model gets it correct. The models were evaluated with these metrics: accuracy, macro AUC, macro F1, which is good for minority classes, macro sensitivity and specificity, and severity weighted AUC, which we created to reflect transition probabilities of escalating. And this is also a good measure of class discrimination. As you can see on the internal validation results, XGBoost was the clear winner in all of these metrics. External generalizability on the EAIC dataset was also tested, and the model did not decrease in performance, notably, so we had high generalizability. We also wanted to see if temporal smoothing of targets. We used first-order hidden Markov model posterior smoothing. We wanted to see if that could improve performance stability. And this is applied on a target to prevent illogical jumps in a target. So, we tested it, and as you can see, there was not a clear improvement in the HMM posterior model, although the macro specificity jumped huge. So, we cannot definitively say it was better, but we can say it was more conservative. Another part of evaluation was curves. The ROC curve and the precision recall curve were both showing great results. And as you can see, the external validation green line, it was not significantly worse than the other lines, so we have a lot of generalizability. There's great discrimination and high precision over broad recall.
After that, we used SHAP. We used SHAP to explain our models. For example, on the right, you can see a graph of each feature's average contribution to the model's predictions, like tidal volume set min, plateau pressure max, and if the patient had any previous support in the last day. On the left, you can see our correlation matrix. You can see that there are very few red squares, indicating that most of our features are quite independent and we avoided multicollinearity. On the right, you can see our SHAP waterfall plots, and you can see which features had positive and which features had a large magnitude relationship and emphasis on the final prediction. Finally, we used machine learning models because they're established and widely recognized in medical research, and we understand that deep learning models like LSTMs and transformers, they're great, but they're harder to explain using tools like SHAP because they're more complex and they're less algorithmic than machine learning models. Here are our final results. XGBoost reached a macro AU ROC of 0.875 on the internal test set, which is very solid. And also, we had great performance on low risk range and high risk range. For high risk range, we had excellent discrimination in the invasive mechanical ventilation. And for the low risk range, you can see on the right, the calibration curve, our model closely follows the 45-degree line. Finally, let's look at our SHAP graph interpreting for invasive mechanical ventilation because that is the most serious and the most important part of our research project. As you can see, the dominant positive drivers are higher plateau pressure, higher set tidal volume, etc. And these make a lot of medical sense and logic because they reflect a pattern of increasing respiratory load, escalating compensatory effort, etc. So our models are very logical and they are very good for doctors and nurses to use.
Let's look at the conclusion. Overall, we showed that XGBoost can accurately predict respiratory support. But we do not want to replace clinician judgment because neither our model nor doctors are 100% accurate. We want them to work together. We want to give doctors a rough heads up of the conditions of the people in the ICU the day before so that resources can be used better. Let's end with some key points of innovation. First of all, we used day-ahead predictions to give doctors time to prepare. We then engineered time series features to give model insights about trends to make more accurate predictions. We also invented severity-weighted AUROC to force the model to emphasize escalations to invasive mechanical ventilation. We then used SHAP to individually and globally explain our model's prediction. In the future, we may use deep learning. We want to thank our parents, friends, and mentors who guided us to success for this project. And lastly, we want to thank the Davidson Fellows Scholarship. Thank you.
Thank you.